So we will be talking about polarization today, particularly with the reference to radio frequencies. But before we do that, let's appreciate how bees have been using this all along. They use the skylight polarization for navigation. The terms used here, Q, U, and so on, is something that we will get familiar with as we go along. But directions will be defined by some specifications of these parameters, which are Stokes parameters, as we will see. So I will spend a little bit of time talking about relevance and motivation, and then we will look at the type of polarization states we come across. We'll see a role of finite bandwidth and integration, and then we will introduce ourselves to Stokes parameters. We will take a brief walk on the Poincare sphere, and then talk about some of the propagation effects, key effects that makes lots of things possible, Faraday rotation, for example, and resulting spectral modulation. And then we will see how these measurements are made in practice and what are the challenges. If I have time, we will briefly touch upon what can lead to depolarization and how to disentangle and overcome that largely in at least one direction, which is the depth, to see if one can conduct some kind of a tomography. You must have seen already various people mentioning aspects of polarization as key pieces of information in the probes that are being done in various directions, various sources. There is kind of richness which is uniquely associated with polarization, and they basically bring us information about the magnetoionic medium conditions in regions of particularly non-thermal emission, which are the primary sources of polarized light. Of course, when I say light, it's across the entire electromagnetic spectrum, including radio. So we also see that in the foreground through which the radiation propagates, we also get to sample those effects. And if there is any emission on the way, we will see it, as well as the foreground, if it has a thermal plasma and presence of magnetic field, it will modify the polarization state of the signal passing through, an effect that we will see, a Faraday rotation. And so it brings us information about the region in between as well. In general, there could be regions where thermal and non-thermal components might exist, where we might have emission produced by the non-thermal component and its polarization property modified by the thermal plasma through which the radiation propagates. So let's look at something which you will be already very familiar with. So apologies for repeating this. So the general case of polarization is that of elliptical polarization, depicted here on the side. This sort of the way. Okay, along the direction of propagation of the wave, if we look down, you will see in projection a trace of the tip of the vector electric field doing a dance, and that locus will define the kind of polarization you associate with that wave. It could be plane polarized in the sense the oscillation of the electric vector might be in the plane containing the direction of motion, or could be across a sort of volume like is shown here, where it does in projection a two-dimensional dance, and in general it would be an ellipse. The linear and the circular are simply the special cases of the elliptical polarization, as you will agree, where the aspect ratios define these two extremes. How do we understand what leads to this elliptical shape? Is a coherent superposition of two orthogonal states of oscillation. If you were to take plane polarized light, which is along the xz, in the xz plane and yz plane separately, and were to do a coherent superposition of it, then you will find that it will trace an ellipse, much like the Lessage's figures that you would have seen on oscilloscope. And so that ellipse, its shape and its orientation would depend on the relation that the oscillation along the XZ plane and the YZ plane would have, both in terms of their relative amplitudes and the relative phase. So either you can express this as superposition of two linear polarizations, or you can also superimpose, you can also think of these as combination of two circular motions in the two senses, the right hand or left hand circular, that means clockwise or anti-clockwise directions, and their relative phase difference and their relative circle radii will decide what the shape of the resultant coherent superposition ellipse would. This need not be confined to circular or linears as a coherent superposition. You can take any two states which are orthogonal to each other, much the same way as you can have, we identified the two hands of circulars and two directions of linears. You could have a combination of part circular, part linear, defining an ellipse, and another ellipse which is orthogonal to it. So for example, if this were to be one state, the other state will be perpendicular to this. So you, for every one state, you can always find an orthogonal counterpart. If you want to take those as pairs, you can also express any other ellipse as a superposition of it. But what we really require then is three numbers somehow to describe the ellipse completely. Either you can express this, as I said, as two circulars, in which case you need to know the magnitude of the fields and the relative phase difference. So I'm indicating that as EL, ER, L for left and right, R for right, and phi LR is the relative phase difference between oscillations in the L and R. You have oscillations occurring at the rate of the frequency, and so it will have this term omega t and a propagation term as well, the spatial. So simple standard wave equation describing these fields, and an additional phase difference relative to of one with respect to the other. Similar thing can, if we were to use linears, we will require again three numbers describing the magnitudes of the x and y and the phase difference. And as I said, any arbitrary elliptical pairs that you would like to choose, which are of course internally mutually orthogonal, you will require again these three numbers. Now, of course, so if you don't like this description, you might want to relate that to things like the parameters of the ellipse, which will be semi-major axis, semi-minor axis, and the inclination of the semi-major axis, or an overall size, and then aspect ratio and theta, this inclination. You might even want to choose a pair thing like amount of circular and the amount of linear polarization and its orientation. Orientation will be the position angle, or might want to express this as instead of magnitude of the linear and position angle, you might want to express that as two components of the linear. So the circular and two linear components. In any case, the main point I'm driving home at is we will require minimum three numbers to define the full state of polarization. So we need at least three measurements, right? And then of course, we also need to know if this is only partially polarized, how much is the total intensity, or what this is a fraction of. So this brings us to the formal set of parameters radio astronomers routinely use, known as Stokes parameters. And here what we define is the total intensity. This is the quantity regardless of the state of polarization, will give us the associated intensity in both the modes, normal and the orthogonal mode, whichever components we are taking. So it could be, in the case of linear polarizations, orientation, some reference orientation, and another orientation 90 degrees away from it. Normally labeled as X and Y. So this is the modulus square of the electric fields associated with it. And you will agree that this will give us the total intensity associated with both the modes. You could also rotate the pair by 45 degrees and get, as long as they're internally orthogonal, you will get the same answer. So this total intensity can be measured in a variety of ways. If you were to have right and left circular instead of the linears, the sum of the two will give you the same total intensity. The Q parameter, the Q and U parameter define the linear polarization components, and the one aligned with respect to X can be, or Y can be defined as the difference between the X and Y polarizations. Depends on which direction you take as the zero orientation, but it's essentially the one with zero orientation. Subtracted from that is the orthogonal. So this is a difference between the two orthogonal linears, and this is the difference between the two orthogonal linears if the system were to be rotated by 45 degrees. And V is simply the net circular polarization, which is difference between these two. But these quantities can also be computed as cross correlation terms. For example, the Q is, for the linears, it's simply the difference between the intensities, but it can be the cross correlation between the left and right circular polarizations and the conjugate added to that. You can work this out and define exactly what those entities will be based on whatever pair you have. Whereas U and V will be the real and imaginary parts of the cross correlation between the two linears. U will give the component which is correlated between X and Y, which can also be obtained by subtracting the 45-degree oriented versions pairs, because the correlation defines the axis. The correlation axis is at 45 degrees between X and Y. Similarly, V will be the imaginary part of the complex correlation between the X and Y. And that's nothing but saying that the X and Y will have a circular combined together, giving rise to a circular motion, will require phase difference of pi by 2 between the two. And that's exactly picked up by the imaginary part of the complex correlation. So this can be simply the difference between the two bands of circular polarizations, or can also be obtained in terms of imaginary part of the complex correlation between X and Y. It's useful to have a tool of visualizing this, and this was provided by Poincaré, where the Poincaré sphere can represent all the states of polarization in the following way. The poles representing the pure circular polarizations at the two ends, and the equator defining pure linear polarization. And as you go along the longitude or along the circumference at the equator, the orientation of the linear is changed from horizontal to being vertical. Of course, you know that the polarization position angle or the orientation requires to be defined only to plus minus 90 degrees. That means a range of 180 degrees, because the same track but traversed in the opposite direction only amounts to a phase shift of the wave by 180 degrees. And so it's not an independent oscillation plane. And so that is captured by the fact that the entire circumference of 360 degrees is representing the range of 180 degrees. So you will find that this horizontal thing will become vertical by the time you got the semicircle on the equator, and then back to horizontal over the next semicircular track. So you will find that the position angle here times 2 is the Poincare sphere longitude. Latitude is, of course, a measure of the amount of circular, and you will find the eccentricity reduces as you go to the poles, becoming pure circular at the two ends. And the two hemispheres representing the two hands of circular polarization. So we can also see effectively that any elliptical polarization can be even here represented as a combination of linear and circular polarization. This is very useful to begin to see if we were to have two polarization states and we were to see superposition of it, or if we were to rotate certain aspects, for example, the orientation of the linear polarization, where we would be, and so on and so forth. There is an aspect of geometrical phase, which I will not go into, but it's something some of the interested people might want to look at. It is more commonly known because one was not aware of Pancharatnam's work, it was known as Berry's phase. And this is geometric phase, where if a wave does walk on the Poincare sphere, in a sense changes its polarization state, a track which can be drawn here, then it states that the wave will acquire extra phase difference equal to half of the solid angle that was associated with this track, and it has fundamental implications. Okay, we'll not go into those details, but I just couldn't resist pointing it out to some of the interested people. So one of the problems with the Poincare sphere was that one couldn't indicate partially polarized light. Their assumption was this radius of the sphere is unity, and that is sort of normalized polarized intensity or total intensity, and there was no way to indicate that. So Pancharatnam extended this for partial polarization and introduced a dot which represents the unpolarized component, and that basically showed the correct way of imagining both the things. For example, so this would be the partially polarized light and some part in the dot, and then fully polarized light will be the full extent of the radius. Because it's difficult to show the randomly polarized light as any other component, because orientation by definition is so it's the net effect is of course going to be a dot, which is what is shown. I will not go into the details of use of it, except to mention that such option exists to visualize the use of Poincare sphere to represent the polarized. The bandwidth plays a very important role in the way we see the signals and their polarization states. Because as you will appreciate, a pure monochromatic wave is 100% polarized. By that I mean it has a given state of oscillation and it continue to follow that. There won't be any deviation from it. Had there been any deviation, it would amount to change or departure from this monochromaticity, and it would acquire some bandwidth. Because more practically, what we encounter is let's take completely randomly polarized light, which we call unpolarized signal. If we look at any given time, it appears to have a certain state of polarization, and that persists for as long as the time which is inverse of the bandwidth. For example, if I take the bandwidth of, let's say, 1 kilohertz, I will find that over a millisecond polarization state continues. If this were to be at 100 megahertz, where the oscillations are taking place at 10 nanosecond scales, I will have large number of cycles where it would continue in the same polarization state. So they will be, that will be the scale of temporal coherence, which is inverse of the bandwidth. And the oscillation rate, of course, is given by the frequency. So the finite bandwidth around the frequency will tell you both the number of oscillations that you will have and the scale on which you will continue to have that oscillation in that state. The state will change after that, but you will find that it's 100% polarized each such time. And the superposition of this from one interval to another is being different and unconnected and unpredictable. That is at the heart of the net polarization being low. So at any short interval, the signals are 100% polarized. So you go in any small section of either the spectral domain or in the time domain, you will find that there is 100% polarization. Is the superposition of these coming from different small pieces, either in time or in frequency, lead to the net depolarization or net component being low if there is no relation between the different parts that you are trying to superpose. Okay. So the same thing is the partially polarized light can again be sort of represented here, where the net component might be something. And so you can think of a spread of the orientation of, let's say, linear polarization across where the tips will lie in this circle, let's say 1 standard deviation region from this mean for this other fluctuating component. And that would, the net result of that will be the component that is shown in the thick line here. And this is what will survive after integration, either over frequency or time. But at any given time, it will have a well-defined direction. So you will find that for it to be able to do that, you will require both spread in direction as well as in the magnitude, as we will see why both these are required simultaneously for any cancellation to occur to give you net zero as far as this shaded portion is concerned. So there is no coherence between the two orthogonal components, whichever pair you might want to take. And we of course know that the electric fields we encounter are complex entities in the sense they have their magnitude and phase. So if we were to have only the magnitude of the electric vector as changing randomly, then you will find that the orientation of the plane of oscillation would be unchanged. So if the electric vector that we have at hand were to be oscillating in magnitude only as part of the randomness, then we will find that the orientation remains same, and there will be a high degree of correlation between the x and y, with the factor defining the correlation will depend on, of course, the angle. If we were to have randomness only in orientation and not in the magnitude of the vector, then you will find that it will lead to anti-correlation, in the sense if the orientation is, as the orientation changes, what x loses is gained by y, and that will lead to well-defined anti-correlation. So in reality, both these correlations, one positive and one negative, are cancelled perfectly by the dance which is done both in orientation as well as in the magnitude. And so you will find that these cancel perfectly and leading to zero correlation that we actually see. So important part is, while we might as a convenience immediately think of the orientation changes, remember that the orientation changes alone will not give you net zero. It will have to be accompanied by, or it might still give you zero, but it will leave an imprint of correlation or in this particular case, anti-correlation between X and Y, which we do not see. And that washing out that potential anti-correlation signature will require simultaneous fluctuation in the magnitude of the vector. Let's look at the impact these things have had in the. So when the pulsars were discovered, the lighthouse model was already on the horizon, in the sense people had proposed that we are looking at rotation of a compact star, and this was called the lighthouse model. One really did not know where the actual radiation was coming from. And this became clear through this famous observations of the Vela pulsar made by Radhakrishnan and Cook, who, let me get the cursor, who observed the intensity of the pulse, which occupied a small region of the rotation period, accompanied by polarized components with high degree of polarization, whose orientation of the polarization ellipse, in principle, or part of the linear, changed systematically through our traverse through the cone, or traverse through the pulse. And this was interpreted as one seeing the orientation of the magnetic field lines defining the direction of the electric vector of the radiation being sampled tangentially by the observer, or the observer remaining fixed, observer sightline remaining fixed, and the cone being rotated past us. Both will have the same effect in terms of the sampling. And you will find the orientation of this magnetic field will in projection look like spokes on a wheel if one is looking down the pole direction. And that helped Radhakrishnan and Cook to propose the magnetic pole model. And that's what we now believe as the region of radiation, and that's where the radiation is produced along the magnetic cones of this compact stars. The exact shape of this, the polarization position angle traverse, is governed by, as I said, the track that we take based on how far we are away from the center of this cone, and how fast are we moving. That will decide the shape of this S-curve, and it's tied up with the inclination angles, which basically tell you how the rotation axis and magnetic axis are oriented, how the rotation axis is oriented with respect to the observer, and so on and so forth. It turns out that this also is description for the orientation of a simple vector. If there were to be a stick attached to the star along the magnetic axis, and you were to see the projection of the stick on the plane of the sky as the star rotated, it would be the same description. This has been seen manifesting in beautiful X-radiation nebula that it produces, and the associated radio nebula around it, which is largely powered by the charged particles and the magnetic field brought in from the pulsar, which, although it begins as a colloidal field, dipolar field, as it's wound well beyond the location where the core rotation stops, it is wound in a toroidal fashion. This one is able to map and see, and you can see the wire cage around the pulsar. This is like a donut scene with some inclination, so you will have to imagine that these are lines along the circumference of the donut at various heights. One has also seen beautiful polarization in supernova remnants. This is a picture of Cassiopeia A at a high frequency, and where you see the dashes showing electric vectors, essentially indicating that the magnetic field is perpendicular to it. We also heard from Judith the other day about polarizations in this quasar, and particularly the jets and so on, and the lobes. In here, I think you will see the orientation of the position angle across these jets, and that has revealed lots of important information about the the flows along the jet, and any other resultant magnetic field that it generates. So the one that is guiding the jet, as well as because of the motions of charged particles, the fields produced from that. One of the effects that is both helps and is unavoidable is the Faraday rotation. This is a simple depiction I have picked up from the Wikipedia, where a plane of oscillation of the electric field changes smoothly across another state, which is relatively oriented with respect to the original state. And the rotation is dependent on the property of the intervening medium, including the distance over which these changes are affected, and particularly to the magnetic field strength. And this is true if the magnetic field has any component along the direction of propagation. So it depends on the line of sight component of the magnetic field. So what we are dealing with is not just empty space with the magnetic field, but we have always magneto-ionic medium, which examples of which are the interstellar medium, intergalactic medium, intracluster medium, intercluster medium, and very close to us is ionosphere. So you can think of this as simple dispersion effect, which you worked out yesterday, which Prakash walked you through. And you can think of two states of polarization into which any arbitrary polarization can be considered as split into and being a superposition of. So you can choose the circular polarizations. And the reason for circular polarization is that it will have a sense of rotation and an equivalent sense of magnetic moment associated with it. And so you will find that there will be two hands of circular with certain magnitude and so on. And if the medium, as it offered different refractive indices to two different frequencies, if it does that, if it does so also for two senses of circular polarization, then you will find that the propagation speeds, the group velocities will be different in the medium for these two hands of circular polarization. It turns out, to be precise, that you can actually find out the cyclotron frequency associated with the magnetic field strength, can correct or add additional contribution to the plasma frequency in terms of the cyclotron frequency, and plus or minus indicating the two hands of circular, and then redo your calculation to find out how much the delay you would get through dispersion at that frequency, the frequency of interest. And you will find that you change the situation only a tiny bit, and the effect is very small, but it results in appreciable phase changes, although the delays associated with that might be really small. A tiny phase change can be seen, and this is what leads to relative phase difference between the two circulars. So for example, imagine the two circulars had begun with equal phase at some orientation. Now you had the phase difference created between them. So let's just move one of them by some angle. Then you will find for them to come in phase again, to define a linear oscillation, you will have to, both of them have to go some angle, which is half of the phase difference created. So the Faraday rotation amount of the change in the orientation of the plane of linear plane of oscillation of the linear polarization, which is what defines the orientation. The circular doesn't have the orientation information, will be rotated by half of the phase difference created by between the two circulars. So much the same way the dispersion changes depends on the frequency as nu to the power minus 2, something that you derived yesterday. You will find This rotation also changes the same way. It depends on frequency to the power -2, which more conveniently is written here in terms of wavelength, and it's proportional to lambda square. And you will find that the amount of change proportional to lambda square is also accompanied by this proportionality constant. Now, instead of only the dispersion measure, which was column density of electrons, NEDS, you also have a weighted component of the magnetic field, weighted by the electron density, integrated over the entire path length. Now, since it's a directional quantity, NE is a scalar, but B parallel is can change sign. And so you will find that there could be situations where you've gone long distance, the magnetic field was strong, but it changed orientation on the way, and the net effect is smaller than what you would have got, much smaller than what you would have got had you integrated NE times modulus of B parallel ds. Of course, that quantity has no meaning, but it'll just tell you the amount of rotation that has taken place, some in one sense and some in the other sense, and the net effect is what we will see. So there could be large distances at which you might see small amount of net Faraday rotation because of cancellation due to reversals in the field. For example, the rotation measure contributed by the ionosphere might work opposite to rotation measure contributed by the interstellar medium. And so it's a net effect that we will see. Of course, as you will immediately appreciate, to know property of what the interstellar medium has done, one should account for the contribution that ionosphere has made, and which also might be changing from day to day, sometimes even from night to day, and in different parts of the Earth as well. Now, use of this information that came from rotation measures, that means the amount of magnetoionic material you have on the way, which has information, combined information about the electron density as well as the magnetic field strength. Fortunately, in the case of pulsars, which are pulsing sources, it is possible to measure the column density of electrons using the effect of dispersion. It is not that the dispersion is not happening for other radiation, unpulsed radiation from other sources, but it's not possible to measure it. The way it becomes possible because of this fiducial feature that we have called pulse, and its delay can be measured as a function of frequency. In principle, it could be measured even for other sources, non-pulsing sources, if there was any variation. Suppose the state of the intensity changed suddenly, then it might become possible to measure the dispersion if one followed that change while it happened simultaneously at all the frequencies at the close to the source. It would appear to have happened with delay as seen by us, and that delay at different frequencies could in principle give us the, but since that is not the normal case and the variations are on much longer time scales than the pulsar pulses for most objects, you will find that dispersion measure is a luxury we enjoy only in the case of pulsars. So that combined with the rotation measure can lead us to estimates of the magnetic field. Using that for various pulsars distributed in our galaxy in sort of half of the sector, us being here and region up to the galactic center, and the closer half of the galaxy. One is able to actually map or constrain the models for field distribution, and one actually shows bisymmetric field patterns more appropriately describing the magnetic field in our galaxy, where the sense of the magnetic field changes its orientation. For example, the field is going that way, the arrow is pointing there, whereas in the next arm region, the field is reversed and keeps alternating like that. So if we were to go and look at any one direction here, you will find the field is oriented in one way here, another way there. So the rotation measure might actually increase monotonically up to this point and then drop and so on and so forth. So interpreting these will require care, and we will look at one of the aspects where this might hurt. So through all this, people have found that the typical field strengths are of the order of microgauss. There is, of course, field not just confined to the plane. There are significant components of the field along the z direction coming out of the paper here. So to do this full state of polarization of a radiation measurements related to that in practice, we need to know what all it has been affected by, how much of Faraday rotation it has undergone, because remember the parameters associated with the radiation are modified on the way before they reach us. We also need to know the way we have treated these signals, how our feed was oriented. For example, our fade, if this were to be the two senses of polarization associated with my nose orientation and lips, while I was looking at the source, I might have rotated my head in certain ways, and the relative orientation of the source field oscillation may be differently viewed by me when it was close to the horizon with respect to when it is overhead and when it is about to set. So the change of orientation of the way I sense it, which is actually has a formal technical name called parallatic angle, and it varies as a function of time about the horizon, and that also depends on both the declination of the source as well as the observer's latitude. So then you have to also see whether my equipment has treated them with equal respect, or whatever treatment given to the two hands of polarizations, two orthogonal states of polarizations, and are they really orthogonal states? Am I making measurements using things which actually have, in terms of orientation, dot product 0, so to say? And then we have to ask whether the rest of the electronics has treated it with similarity. If there is any crosstalk, they ideally, I want to measure them in various form without mixing them, having gotten them as orthogonal components. But if there is any mixing, you will find that a bit of Y has gone into X and a bit of X has gone into Y. And that can easily happen with the simplest of the example, where the two sensors that are supposed to be orthogonal are not orthogonal. They're different angle than 90 degrees. And then, of course, you compute the Stokes parameters using the equations I showed, which is a standard way of doing it. So the overall fidelity, in addition to the fidelity compromise due to inherent noise, is decided by various of these factors. This is just an example of how the parallactic angle changes. I have not spent much time on it, except to show that it depends on the declination, the different colors showing, and it depends on the kind of mount. For example, the UT telescope will have no variation of the parallactic angle, in the sense that you look at the source with the same orientation. Flip through this is just the equation describing that. It's a simple geometry. Apart from removing the offsets in the measurements of whatever total powers you measure, other than the cross correlations, you will find you also need to calibrate the gains and leakages and so on, if there are any. And there are ways to do these measurements. These are basically 4 entities you need to decide at each frequency. 2 numbers for complex gain differences, which can be the ratio of the gains, and the complex leakage defining how much of one leaks into the other. But there are some invariant quantities which you can identify, which are independent of the gains being different or even changing. But that's not true in the presence of leakages. Another front, you can use quantities like unpolarized component, which might be free of RFI, the RFI that you heard about yesterday, because most of the man-made RFI is highly polarized and can be removed if your source happens to be largely randomly polarized. I won't go into details of this, but it's useful to observe a randomly polarized source to study the effect of leakage because ideally it should not show any polarization. And because of the leakage, if it starts showing some correlatedness between the two components, that is a good measure of getting your hands on the estimate of the leakage. You, of course, would like to observe a polarized source with known properties and make sure that you see it the way you expect to see it, and the deviations can be used to characterize your system non-idealities and so on and so forth. This can be done even through the feed rotation, which the newer telescopes are now incorporating. The important part here is that whatever you do everything in the reverse order. The last effect that you have enforced on the signal is corrected for first, and so on and so forth. And so that's how the last effect you correct for is estimation and correction of Faraday rotation. Before that, of course, you would have corrected for the telescope orientation. Before that, feed response. And first correct thing you correct is the response of the receiver, the electronics. Okay, so I will stop here.